It's recording. Okay. Let me just make sure. All right, so let's continue our discussion of the ideal gas law. This time we will apply it to counting of gas particles. Now, remember the ideal gas law says PV equals nRT. So our focus in this lesson is this N right here, number of moles of gas particles. Exactly what do we mean when we say gas particles? When we use the word particle, in this context, gas particle, we use this term as a generic way of referring to either a molecule, which would be atoms that are bound together, or non-bonded atoms. So if we were counting gas particles, a molecule would count as just one particle. Okay, a single atom by itself, unbonded to any other atom, would also just count as one particle. Okay, so a free atom counts as one particle, a molecule counts as one particle. So for example, if I were to tell you which one has more gas particles, a mole of methane or a mole of HE, then the answer is the same. The 1 mole is 1 mole, right? Although there are more atoms in CH4 because each molecule has 4 particles, so CH4. Each one of these set of 5 atoms, 1 carbon and 4 hydrogen, will just be counted as 1 particle. So 1 molecule counts as 1 particle, and 1 atom unbonded to any other atom would also count as just 1 particle. So that is what we are counting in the equation PV equals nRT. Okay, the number of moles would be the total number of moles of particles, whether they are atoms or molecules. Each atom counts as 1, each molecule counts as 1. Okay, so how do we actually count gas particles? Like I said, we use PV equals nRT. So all we have to do is measure pressure, volume, and temperature. And R is a constant that we know, you should know. Okay, it's something that's been determined experimentally, so you can solve for N. How do you solve for N? Divide both sides of this equation by RT, right? So you say N is equal to PV over RT. And like I said, this equation is really, strictly speaking, valid in the limit of low pressure. Typical ordinary conditions, you might be in error by as much as no more than 1% under ordinary conditions. So it's a good equation to use. Okay, so the value of R in this case, okay, depends on what unit you use for pressure and temperature and volume. Okay, so if you're using liters for volume and you're using atmospheres for pressure and temperatures in Kelvin, then the value of R is going to be 0.08206 liters times atmosphere per mole per Kelvin. Okay, so that's the unit for R. It's a complicated unit because all of these when you plug in all the numbers here, you should end up with moles. All right, so that's what you'll need to do to calculate moles of gas. So let's illustrate that with a problem. Sample problem here. STP, standard temperature and pressure, so that abbreviation you need to be familiar with, refers to 1 atmosphere and 273.15 Kelvin. So 273.15 Kelvin is 0 degrees Celsius. Okay? So what would be the number of moles of gas particles that would be present in a 22.4 liter sample at STP? Then you're going to say, okay, I want to solve for moles, so N equals PV over RT. So my pressure is 1 atmosphere. I'm just going to treat that number as exact because it's defined as standard pressure. Okay. Volume is 22.4 liters. It's given 3 sig figs here. R, what is our R? Go back to our previous slide. 0.08206. Okay, so that, by the way, I expect you to memorize that, and because you use it so much, okay, 0.0820, you might as well memorize it. 0.08206 liters times atmosphere per mole. You can also write per mole like this, per Kelvin. Okay, and our temperature is at STP 273.15, so 273.15 Kelvin. Okay, that's an exact number. That's the definition of STP. So K cancels out, liter cancels out, atmosphere cancels out. You have 1 over mole in the denominator, so the final unit here, when we do the calculation, will be in moles. So if you did this, what are we going to get? Let's do that. 22.4 divided by 0.08206 divided by 273.15, and that gives us 0.999. Okay, that's essentially 1 mole. Okay, 1.00, or you can say 1.00 mole. So, in fact, that's a good number to remember. A good way to estimate how many particles of gas you have in a sample is to think about 22.4 liters at STP. Okay, so a mole of gas particles will occupy a volume of 22.4 liters at STP. So if I were to tell you, here's an empty bottle of soda, a 2-liter bottle of soda that I just bought from Walmart, okay, empty. How much air molecule is in? How many air molecules are in there? Approximately. You'd say, okay, let's just. We're close to we're close to STP, okay? So not quite at STP. We're at 298 Kelvin, but that's close enough. That's only like a very small percentage difference. So let's just say we're at STP. So 24 liters, if I have about 12 of these, about 11 or 12 of these, of these bottles, I have a mole. So that's going to be about 1/11 or 1/12 of a mole, right? So 1 divided by 11. So I'll have about 0.1 mole. So a tenth of a mole of molecules in there. Okay, so that's how you would use that for estimation. But of course, if you want to do the calculation, you can just go ahead and do the calculation. You can just plug in 2 liters here instead of 22.4 liters. So if you plug in 2 instead of 22.4, then you get about a tenth of the original amount, so about 0.1 mole. All right, let's talk now about what's known as Avogadro's law. Okay, Avogadro's law. Before we mention that, let's just define a couple of things. When we say molar volume, that means volume of 1 mole. Okay, so the molar volume of a gas would be the volume that will be occupied by 1 mole of gas particles. So volume per mole is simply the actual volume divided by the number of moles. Anytime you have something per something, then you divide something by the other something. So volume per mole would be volume divided by number of moles. Okay, and the unit for that, as you can see, is liters per mole. Okay, unit for volume over unit for moles. Now, what would be the molar volume if the gas is behaving ideally? Well, you start with PV equals nRT. You rearrange it. Okay, PV equals nRT. We rearrange it. We want to solve for V over N. So I divide both sides by N. Okay, that gets rid of the N. And I divide both sides by P. So this gets rid of the P on one side. So V over N is RT over P. Okay, so the molar volume of an ideal gas is RT over P. Now, a consequence of this definition, okay, what this equation is telling us is that if temperature and pressure is constant, then you can see that the right-hand side of this equation is constant. RT and P are constant. Then you say that V over N is a constant. Anytime the ratio of two quantities is a constant, okay, that means they are directly proportional. If one goes up, okay, so for example, if this was doubled, then for the ratio to remain constant, I also would have to double the numerator, right? So if one is doubled, the other is doubled. So as number of moles goes up, you would expect your gas to occupy more volume at the same temperature and pressure. So in a way, you can use the volume of a gas. For as long as you have the same temperature and pressure, you can use the volume of a gas as a way of determining how many moles you've got. Okay? The bigger the volume, the more moles of gas you have. So if I were to ask you, for example, an obvious question right here. You have a 2-liter bottle of soda, empty bottle of soda, no soda in there, just air, versus a 1-liter bottle. Which one has more molecules? And the answer would be the 2-liter bottle, twice as many molecules as the 1-liter bottle. Okay? Number of moles is directly proportional to the volume. So this relationship is known as Avogadro's law. Avogadro's law says at constant temperature and pressure, the volume of the gas is directly proportional to the number of moles. Okay, or the molar volume of a gas is constant. So you can also say, you can use this equation to solve problems at dealing with gases at constant temperature and pressure. V1 over N1, if there's going to be a change in either of these two, then if you end up with V2, a volume of V2, you divide that by the final number of moles, N2, V1 over N1 equals V2 over N2. Okay? Now, another way that Avogadro's law can be stated is to say that equal volumes of gas at the same temperature and pressure will have equal number of particles. Okay? Or you can say at the same temperature and pressure, all gases will have the same molar volume. Why is that? Molar volume is RT over P. Same T, same P. It doesn't matter what kind of gas you have. It can be made up of atoms, made up of molecules, made up of a mixture of atoms and molecules. If you can count all of those particles, provided you're looking at the same temperature and the same pressure, the ratio of the volume to the number of moles, the molar volume, would be the same. In fact, we just showed earlier that at STP, that molar volume is going to be 22.4 liters per mole. Now, at room temperature, the volume is going to be a little larger, right? STP, remember, is at 0 degrees Celsius. That's at the freezing point of water. At room temperature, which we would normally call SATP, okay, the molar volume is about 24.8 liters. Okay, so that's about 25 liters. SATP, okay, that's more common condition you'll encounter because that's typical room conditions. The A here means ambient. That means the prevailing temperature and pressure. So standard, ambient temperature and pressure. So the molar volume of gases at standard ambient temperature and pressure is about 25 liters. It's 24.8. So it's kind of easy to remember. It's close to 25, so it's a good thing to remember. All right, so let's look at a couple of examples here. Which of the following samples will contain the most number of gas particles at the same temperature and pressure? Okay, so same temperature and pressure, so volume is directly proportional to number of moles. By the way, this symbol right here, that means directly proportional. Okay, so V over N is a constant. Okay. All right, so is it sample A, 2 liters of methane? Sample B, 1 liter of H2. Sample C, 2 liters of helium. Or sample D, 4 liters of helium. Which one would have the most number of gas particles? A, B, C, or D? Very good. All right, it doesn't matter what kind of gas particles you have. If you're just counting particles, you have more moles of particles if you have a bigger volume, provided you're comparing gas samples at the same temperature and pressure. And that is Avogadro's law. Okay? How about this one? Which of the following gas samples contains the most number of atoms at the same temperature and pressure? So we're not just counting particles, we're counting number of atoms. Sample A, B, C, or D. Okay, let me give you a little hint. Have you started collecting the responses? All right, let me give you a little hint. Let's say this has X moles, okay? Then twice as much volume, you're going to have 2x moles of particles, right? And this is going to have 2x moles of particles, twice as much volume. And this is going to be 4 times the volume of sample B. You have 4x moles of particles. This is particles, right? And a molecule counts as just one particle. How many atoms does this sample A actually have? How many atoms does sample B actually have? How many atoms does sample C actually have? And how many atoms does sample D actually have? So what would be the answer for this one? D? Okay. All right. Okay. Everybody said A. Why? Because the actual number of atoms, you have to multiply this by 1. You have to multiply this by 5 atoms per molecule, right? Because what the actual count 2x here would be the number of molecules, since CH4 represents molecules. So 2 times 5, that would be 10x. Okay, this one on the other hand would be, you multiply that by 2 atoms per molecule. So that's going to be 2 times 1, that's just going to be 2x. And this is just still 2x, and that would still be 4x. So A would have the most number of atoms. But as far as number of moles of gas particles, sample D would have more gas particles. All right, let's talk about mixtures now. Okay. And when we're dealing with mixtures, we can define what is known as the partial pressure. Okay. So before we do that, let's just go back to our ideal gas equation. For any gas, okay, we said whether or not it's pure or whether or a mixture of different particles, if it's behaving ideally, you say that the equation PV equals nRT is obeyed. So if you want to solve for pressure from this equation, what would you do? You would divide both sides by the volume, right, to solve for pressure. So your pressure is going to be equal to nRT over V. That would be the pressure of a gas if it has n moles of particles in it at temperature T and it occupies a volume of V. Now, partial pressure is something we define for a component of a gas mixture. So if you have a gas mixture, a component, let's say component A, we can define the pressure, partial pressure of component A as number of moles of A times RT over V. Look, compare these two formulas right here. This is the total pressure, and this is the total moles. Okay? Now, if you want what's called the partial pressure of A, instead of using the total moles, we just use the number of moles of A, just the moles of component A, and then you still multiply by RT over V. You get what's called the partial pressure of component A. So how would we define partial pressure based on this mathematical definition? You would say, in words, you would say partial pressure would be the pressure. And let me erase this. It's the pressure that a component of a gas mixture would exert if it were alone. So if we were to remove all the other gas particles, then the pressure would be just moles of A, which is what you're interested in, times RT over V. Okay, so the partial pressure of a component of a mixture is simply the pressure that it would exert if it were alone in your container. Okay. So let's illustrate that with this example. What are the partial pressures of oxygen and nitrogen in a 25-liter sample containing a mole of oxygen and 4 moles of N2 at 300 Kelvin? Well, let's see. Partial pressure of oxygen would be, the formula is moles of oxygen times RT over V. Okay? Remember, PV equals nRT. We can rearrange that to P equals nRT over V. All I have to do is plug in the numbers. So what do I have here? Moles of O2 would be 1 mole. Okay. And what is R? 0.08206 liters times atmosphere per mole per Kelvin. What's our temperature? 300 Kelvin. What's our volume? 25 liter sample, so our volume is 25.0 liters. Okay, and let me solve this. What's RT over P? Pick up my calculator here. 0.08206 times 300 divided by 25. That's 0.9847, so 0.985, okay? 0.985. Okay, so I have liters cancel out, Kelvin cancels out. Okay, so that would be, this number right here would be atmosphere per mole, and multiply that by 1 mole. So 1 times 0.985 will be 0.985 atmospheres. Okay, so moles cancels out. So that's the partial pressure of O2. Same thing, if you want to calculate the partial pressure of N2, what would you do? You write the same formula, except you're using N2. So partial pressure of N2 is moles of N2 times RT over V. Okay? And we already know RT over V. How many moles of N2 do we have in this question? It has 4 moles of N2. Okay, 4 moles of N2. So 4.00 moles of N2. And our RT over V, we've already figured that out earlier. That's why I calculated that separately. It's 0.985 in this case, atmosphere per mole. So 4 times 0.985 would be 0.985 times 4, that gives you 3.94 atmosphere. So that would be the partial pressure of nitrogen. Okay, so that would be your partial pressures. Okay, now what would be the total pressure? Can we just add up the two? Let's see. We can actually calculate the total pressure. The total pressure is total moles times RT over P, RT over V, right? What's the total moles? Total moles is 1 mole of O2. Okay, total moles is a mole of O2 and 4 moles of N2. So I can just add those two numbers. I can get the total of 5 moles. And I already know my RT over V is 0.985, right? Atmosphere per mole. So what's 5 times 0.985? 4.925, so 4.93, okay? Atmosphere. Is that the same number you get if you just added the two? .985 plus 3.94. Of course it is, right? In fact, mathematically, you can show that that is the case because here's a way you can do that. You can say the total pressure okay. You can say your total pressure is equal to moles O2 plus moles N2, okay, times RT over V. This is the total moles right here. That's your total N, right? And so using the distributive property, I can multiply this and multiply that. I can get moles O2 times RT over V plus moles N2 times RT over V. Well, what is moles O2 times RT over V? This is just the partial pressure of oxygen, and moles N2 times RT over V is just the partial pressure of nitrogen. So you can just add up partial pressures to get the total pressure. So that is known as Dalton's law of partial pressures. Dalton's law says the total pressure of a gas will just be equal, a gas mixture will just be equal to the sum of the partial pressures of its components. Okay? So for a gas mixture, okay, here it is. Here's a general derivation of that. PV equals N total times RT. So I divide both sides by volume. So divide both sides by volume. V cancels out. So pressure is total moles times RT over V. But total moles is moles of component A plus moles of component B and so on times RT over V, and then you distribute. This gives you partial pressure of A, N sub A times RT over V plus partial pressure of B and so on. So the total pressure of a gas mixture is equal to the sum of the partial pressures of the components. Okay? That's Dalton's law of partial pressure. Here's a common setup in the lab where you would need this type of information. Okay, if you have an enclosed vessel, okay, well let's put an open vessel first. Let's say you have a beaker and you put some water in it. Okay, what happens to the water eventually? It dries out, right? It evaporates. But what would happen if I were to close it up? Okay, then the water molecules go into the gas phase, right? But then the gas molecules in the gas phase can go back to the liquid. Remember, molecules are always moving. So ultimately, you reach a situation where the rate at which the water molecules leave the surface is equal to the rate at which the molecules from the gas go back to the liquid. So you would establish, okay, ultimately you would establish a constant partial pressure of water molecules in the gas. This constant partial pressure that you obtain at a given temperature, right? And this partial pressure that you get depends on what the liquid is. In the case of water, at room temperature, if you leave it alone for a while, let it sit at room temperature, 298 Kelvin in an enclosed container, it's going to build up to 23.8 torr, and it will stay there. It's going to be a constant at 23.8 torr. This value right here, 23.8 torr, we call that the vapor pressure of water. Okay, so this pressure of the gas here, that's, we say, in equilibrium with the liquid. So you say gas is in equilibrium with the liquid. We have what's called a dynamic equilibrium. That means the rate at which molecules go back to the liquid is the same as the rate at which the liquid leaves the molecule. So it appears as though there's no change. So the pressure of your gas would remain constant. That pressure right there is called the vapor pressure of water. Okay, so that's the vapor pressure of water. Now, in one of the experiments I posted that you could be doing, you will generate hydrogen, but you're going to collect it over water. Hydrogen, H2, is not soluble in water, so it's going to bubble up. So you're going to invert a burette, and it's going to be closed up here. Close the burette up there. And you'll have some water. okay, filled with water. Actually, vinegar, you're going to be using vinegar, and you'll have a reaction here. Vinegar is just acetic acid in water. A reaction will generate hydrogen, so you'll be able to collect hydrogen gas. So in here, you'll have hydrogen gas, and here you have water. Okay, so your hydrogen's going to bubble up into your burette. Okay, and what you have down here is just water, so you have a beaker of water here. Now, this hydrogen gas right here that you have is not pure hydrogen. It actually has water vapor. Okay, because you're collecting it above water, so it actually will have, in addition to H2 molecules, it's also going to have H2O molecules there in the gas phase. So one of the things you'll be calculating is you would be interested in the partial pressure of the hydrogen. So you need to be, if you can measure the total pressure of the gas in there, you have to subtract the vapor pressure of the water to figure out what the partial pressure is of the hydrogen. So in this case, okay, let's say you collected a sample and you found the pressure to be 750 torr. So what if you did this experiment and you found that the total pressure is 750.0 torr? Okay, what's the partial pressure of hydrogen? And this is a very simple problem actually. All you have to do is to get the partial pressure of hydrogen is you subtract the vapor pressure of water from the total pressure, because Dalton's law says partial pressure of hydrogen plus partial pressure of water vapor must be equal to the total pressure. This is Dalton's law. So if I want to know what is the partial pressure of hydrogen, then I have to subtract, okay, the partial pressure of water from the total pressure. So partial pressure of hydrogen equals the total pressure minus the vapor pressure of water. And my total pressure, according to the problem, is 750 torr. And the vapor pressure of water at room temperature, okay, according to this, is 23.8 torr. This is a number that you can look up from tables. Okay, let me see if I can do a quick lookup for you. You can just Google this. You say vapor pressure of water, and you can even find it at different places. So let's see. This is the Wikipedia. Okay, there it is, 23.8 at 25 degrees Celsius. Okay, 23.8 torr. Right. There's a variety of other sources. If you don't trust Wikipedia, you can check other sources. Okay, this is okay. You can go to websites that have a .edu domain name. For the most part, I find that Wikipedia is quite reliable if it has nothing to do with opinion, if it's just dealing with facts, especially scientific facts. Okay, you don't expect malicious people to post wrong information there. Here's 23.8 torr at 25 degrees. Okay, that's at Oklahoma State. So there's a whole bunch of websites where you can look this up. Okay, and it depends on what the temperature is. Here's Georgia State University. Vapor pressure of water at 25 degrees is 23.76 torr. This is millimeters of mercury. Okay. So anyway, that's a number you can look up on a test if you don't have access to or you can also look it up from handbooks. If you don't have access to a data source, that would have to be given to you on a test. So anyway, the total pressure minus the vapor pressure of water would be 750 minus 23.8. That gives you 726.2. By the way, a good authoritative source for vapor pressure, and have this in one of your lab activities, I have this information, is at the NIST website. So you just search for web book, go to webbook.nist.gov, okay? And when you get there, click on Chemistry Webbook, okay? And when you get to Chemistry Webbook, what you can do is click on Formula, and you can enter H2O there, okay? And you can get information, as much information as you want. Click on these types of information that might be available. So you want gas phase, condensed phase, and phase change data, okay? And so you have different isotopic compositions of water. So you have one that has deuterium in it. So just get the regular water here. And you'll see here, there's a formula for, let's see, where's the vapor pressure information here? Here, you got the boiling point of water, 373 Kelvin. Okay, and here's, if you look for what's called the Antoine equation parameters, that tells you how the vapor pressure depends on temperature. Okay, so from 379 to 573 Kelvin, you can calculate it using this equation. Log of the vapor pressure is equal to A minus B over T plus C. And the values of A, B, and C are given in this table, depending on what temperature range you're interested in. So you can calculate the log. Once you figure out the log, just take the anti-log, and that will give you the actual pressure. Okay, so that's a good source of data for vapor pressure, NIST webbook, and for a whole bunch of other information that you might need. Okay, so this is 760.24. All right, let's continue. Partial pressure and mole fraction. Let's define mole fraction. Mole fraction is defined as just the ratio of the moles of components of a particular component to the total number of moles. So mole fraction of component A would be how many moles you have of component A, divide that by the total number of moles. That gives you the mole fraction. So if you add up all the mole fractions of your components in a mixture, they should add up to 1, right? Because if you have moles of A plus moles of B plus moles of C and so on, okay, over total moles, over total moles, over total moles, then if you add them all up, then you just get N total over N total. That will just be equal to 1. So all mole fractions should add up to 1. Just like percentages should add up to 100%, fractions should add up to 1. Okay? Mole fractions add up to 1. Now, for a gas mixture, okay, the partial pressure is of component A is moles of A times RT over V. We saw this earlier. But the total pressure is total moles times RT over V. So what happens if I divide partial pressure of A by the total pressure? Okay, then that gives me moles of A times RT over V divided by the total moles times RT over V. This means that, okay, I can cancel RT over V, but what is moles of A over moles total? That's just mole fraction of A. So if you want to know what fraction of the molecules in your gas sample is A, if you have somehow a way of finding out what the partial pressure of A is, then you can just say the mole fraction of A would be whatever the partial pressure of A is divided by the total pressure. Okay? So that's a good way to determine how much you have in your gas sample. So if you have, like, let's say you found out your mole fraction was 0.2, then if you had 25 moles, then the actual number of moles will be 0.2 times 25. Whatever total number of moles you have, so from this, one useful piece of information you can get is you can get the actual number of moles of A, which is just the mole fraction of A times the total number of moles. Okay? So that's a good way to get to the composition of your mixture. Here's an example. About 21% of molecules in a typical air sample are O2 molecules. So the air you breathe is mostly N2 molecules. It's about 78% N2. 21% of those molecules are O2 molecules. So we say that the mole percent of oxygen is 21%, or you say that the mole fraction of O2 is 0.21. 21% is the same as 0.21. Okay, so what's the partial pressure of oxygen in the air sample if you were to have a pressurized air sample of 1.2 atmosphere? Then you just say, okay, partial pressure of O2 would be equal to 1 divided by the total pressure, would be equal to mole fraction, right? Mole fraction of O2 is partial pressure of O2 divided by the total pressure, which is given to be 0.21. So I know my total pressure is given as 1.2 atmosphere, so that's 1.20 atmosphere. So I should be able to solve for pressure of O2. Or I can write it this way. I can say partial pressure of O2 is mole fraction of O2 times the total pressure. Okay. I'm just rearranging this equation. I multiply mole fraction of O2 times the pressure, multiply these two, that gets partial pressure of O2. So this gives me 0.21 times the total pressure of 1.20 atmospheres, and that gives me 0.21 times 1.2, or 0.252. 2 sig figs, so I should only keep 2 sig figs. I have to drop that one. So it's 0.25 atmospheres. Okay? So if your sample was only 1 atmosphere, then it's going to be 0.21 atmosphere of oxygen. All right. Now that we know how to count gas particles, we can extend our lesson on stoichiometry to involve reactions that have gases in them, that involve gases. Okay? The same idea. Changing the moles of gaseous reactants and products, like I said, you can now determine from pressure, volume, and temperature data. Okay, and so if only one product or reactant is involved, only one reactant or product that's involved is gaseous, you can calculate the number of moles of that gas to be PV over RT. Now, if you have to deal with mixtures, you're going to have to use Dalton's law to solve that stoichiometry problem. Okay, so let's illustrate that with this problem right here. Suppose you have 22.4 liters of carbon dioxide generated at STP by decomposing sodium bicarbonate. So you have a reaction here with one reactant producing 3 products. So that's a decomposition reaction, remember? Okay, so now let's say that 22.4 liters of CO2 were collected at STP. How much Na2O was produced? Okay, so if I want to know, what am I given? Liters of CO2. So at STP. Okay, by now you should know that you should be able to figure out moles of CO2 from that one. Okay, so you can figure out moles of CO2. What am I looking for? Moles of Na2O, so I have to figure out moles of Na2O from that. What information would I need to go from mole CO2 to moles Na2O? I would need the mole-to-mole ratio as given by the coefficient in the balance equation. You have 2 moles of CO2 gas produced for every mole of Na2O that's produced. So the question here says how much Na2O was produced. So let's solve this problem. First thing we do is convert liters of CO2 to moles of CO2. Quick way to do that is, okay, moles of CO2, N is equal to PV over RT, right? What's our volume? 22.4 liters. So our pressure is 1 atmosphere, STP. Our volume is 22.4 liters. R is 0.08206 liter atmosphere per mole per Kelvin. Our temperature is 273.15 since it's STP. And we've already done this calculation before. This is 1 mole of CO2. Okay? 22.4 liters at STP is 1 mole. So if I know I got a mole of CO2, how much Na2O did I get? Then I'm just going to say, okay, 1.00 mole CO2. Okay, according to my balance equation, 1 mole of Na2O is also produced if I produce 2 moles of CO2. Okay, where did I get this 1 and 2? The 2 is the coefficient of CO2 here. All right, and the coefficient of Na2O is 1, so that's that 1 down there. So if I got 2 moles of CO, 1 mole of CO2, then I would expect to have gotten half a mole of Na2O. Okay, moles of CO2 will cancel out. That makes sense. I get 2 moles of CO2 for every mole of Na2O that I also get. So if I only got 1 mole of CO2, I only get half a mole of Na2O. All right. Now, if you want to know how many grams that is, then you'll just have to change that to grams. How do you change moles to grams? You're going to need the molar mass, right? So 1 mole of Na2O, and I need the molar mass over here. Okay, so what's the molar mass of Na2O? It's 2 sodiums, so that's 2 times 22.99. And an oxygen is 1 oxygen, so that's 1 times 16.00. So let's see, 2 times, oops, 2 times, let me clear this one, 2 times 22.99 plus 16, 61.98. Okay, so this is 61.98 grams per mole. So this would be 61.98 grams of Na2O per mole of Na2O. And so that should give me an answer of half of 61.98. So 61.98 times 0.5, 30.99 grams. Okay, so I'm going to get 30.99 grams, 3 sig figs. So I need just 31.0 grams of Na2O. Okay, so you can extend our stoichiometry lesson with by doing these types of calculation. Here's an example that involves gas solutions, gas and solutions in stoichiometry. This is in fact similar to what the experiment is in the lab. You have magnesium plus hydrochloric acid will give you hydrogen gas. So what you're going to do is you're going to react HCl, okay, an aqueous solution of HCl. You're going to put magnesium in there, stick a magnesium ribbon in there, and it's going to bubble out. So this will originally be filled with liquid, and then as your H2 is produced, it will displace the water, it will displace the liquid, and you end up with that H2 collected inside that tube right there. Okay, but that H2 is wet. Okay, so it's got water vapor in it because it's collected over water. So suppose the volume of the gas collected at room temperature is 2.5 liters. Okay, and the water level inside the tube, let's say this happens to be 10 centimeters above the water level outside. Okay, so that's an extra, you need to know the pressure of that column of water. And the prevailing barometric pressure is 755 torr. So you have a pressure of 755 torr on the outside from the atmosphere. The question is, what's the question here? How much HCl was consumed in this reaction? Well, to figure out how much HCl is consumed, you have to first figure out how much H2 was produced, because all the information given to you here will allow you to figure out moles of H2. So let's figure out how many moles of H2 did we make. So we need moles of H2 is equal to P partial pressure of H2 times volume over RT. Okay? Do I know the volume? Yes, I know the volume. It's 2.5 liters. So this volume right here is 2.50 liters. I know what R is, right? What's the value for R? 0.08206 liters times atmosphere per mole per Kelvin. Do I know my temperature? This experiment was done at room temperature 298 Kelvin. So I know my temperature is 298 Kelvin. So for me to figure out moles of H2, I have to figure out the partial pressure of H2. Okay? So the question is, what's the partial pressure of H2? Well, let's see. You're collecting H2 over water. So here you would have the pressure due to the atmosphere is 755 torr. Okay? That must be equal to the pressure due to the gas plus the pressure due to the column of water. Okay? So pressure of the gas plus pressure due to the water column must be equal to the atmospheric pressure or the barometric pressure. So barometric pressure is 755 torr. Okay. So pressure of the gas I can calculate from this equation. Well, what else do I need to know? I need to know that the pressure of the gas is not just H2. It's actually what? This pressure of the gas is partial pressure of H2 plus the partial pressure of water vapor. Okay? And then I add to that the pressure of the water column. That would be equal to the barometric pressure. Right. So this is what I need right here, partial pressure of H2. I know this is 755 torr, the barometric pressure. The water vapor pressure at 298 Kelvin is 23.8 torr. That's the vapor pressure of water. How do I get the pressure of a column? Density times G times the height of the column, right? Or a shortcut I can use for water columns, okay? Water columns, the pressure due to a water column, okay? 1 millimeter of water column actually 1 millimeter of mercury is equivalent to 13.6 millimeters of water column. That's a good conversion to know. That's simply because the density of your mercury is 13.6 times bigger than that of water. Density of water is 1, density of mercury is 13.6. So your water column is not going to exert as much pressure as a mercury column. So this, instead of using that formula, you can just say the height of the water column. So that's the pressure in millimeters of water. You just multiply that by 1 torr, which is 1 millimeter of mercury, is 13 divided by 13.6 millimeters of water. So you just divide that height of the water column by 13.6. Okay? And so that's how you'd figure that calculation out. I'll leave that calculation up for you to finish up. See if you can get a final number for me. Okay? Let's see, there's a few more things we need to cover in this chapter. Let's see, determining molar mass. All right, but doesn't seem like we're going to have enough time. So let me see if I can just try to finish up that calculation for you. So what do we have here? What's the height of the water column? Height of the water column is 10 centimeters above the water level outside. So that's 100 millimeters of water. Okay? So we're saying then that the water column right here is 100 divided by 13.6 torr. So from this, you can calculate the partial pressure of H2. So partial pressure of H2 is equal to the total pressure 755 minus the water vapor, which is 23.8, minus 100 over 13.6, which is the water column. All of this is in torr. Okay, so 100 divided by 13.6 is 7.35. Okay, so 755 minus 23.8 minus 7.35, that gives you a total of, what would that be? 755 minus 23.8 minus 7.35, that gives me 723.9 torr. And I can change that to atmosphere. 1 atmosphere is 760 torr. So the partial pressure of H2 is 723.9. Oops, what did I just do? Okay, click on the wrong thing. 723.9 divided by 760. That's 0.952 atmospheres. Okay, so this is going to be 0.952 atmospheres. So I have my partial pressure of O2. I solve for moles of O2. So it's going to be PV over RT. So 0.952 atmospheres. The volume, according to the problem, is right here, 2.5 liters. 2.50 liters. R is 0.08206 liters times atmosphere per mole per Kelvin. And the temperature is 298 Kelvin. Okay? So if we do that calculation, that gives us 0.952 times 2.5 divided by 0.08206 divided by 298. And that gives me 0.0973 moles of H2. This is H2. Moles of H2. So if I know my moles of H2, I can go back and figure out what am I looking for. How much HCl was consumed, right? So the question here is how much HCl was consumed. So I need the H2 to HCl ratio is 1:2. 1 mole of H2 for 2 moles of HCl. So I multiply that. 0.0973 moles of H2. Okay. 2 moles of HCl for 1 mole of H2. And that gives you, okay, let's just verify. It's 2 moles of HCl for 1 mole of H2. All right. So 0.0973 times 2 divided by 1 is 0.195 moles of HCl. So that would be the answer. That would be the amount of HCl that was used up in this reaction, 0.195 moles of HCl. Okay, So we'll finish up this presentation next time. We got a few more slides to go, but I think we'll stop here for today.